a second. Yeah, when I started this, I was on the very early Azure sales team. And so that's how Bill and I came together. He was a customer. I was just figuring out what this thing was about. Literally that year when they hired us, there were 4 of us, and they said, go figure out how to sell this thing. So then they decided they knew better how to sell it. So things are a little weird right now, which is why I'm still doing the same slide deck. Well, it's not the same slide deck. Some of these pictures, if you've seen this before, you'll recognize it. You know, some of it I've had for quite a while, and the weird thing is after 10 years in that it still seems to be relevant, which just got 2 sides to it as well. Normally in our industry, if something hasn't really kind of grabbed the big value proposition within a few years, we rebrand it and we go on. We call it something different and we keep going. Cloud has actually been quite tenacious. I mean, it's a 15-year-old conversation and we're still talking about it. We've just wrapped a bunch of other stuff around it. So slides are showing okay?
Yep, yeah. I can see them.
Okay, thanks. All right. So also the kind of the design. So I do work for Microsoft still. I'm in I was called an application development manager until a few months ago. I'm an account manager who manages developer support contracts, and the developer world wound up eating the whole, you know, in the cloud space, wound up not being just about application architecture and code. It wound up, you know, we have infrastructure as code, which I'll talk about that in a few minutes. We have DevOps, you know, so there's dev involved in that, and it's really dev tooling being applied to ops problems. Among other things. And it's just a whole language that we in the development community speak that the traditional Microsoft infrastructure space, they just really don't know anything about it. So I've gleaned a lot of these lessons, starting with opinions and now kind of validated in the field in front of customers. You will hear me say things that are not in alignment with messaging you will hear from Microsoft. I think Microsoft's, you know, mistaken in some of the ways that we're putting this forward, and it has to do with what our customers want to hear versus what the actual cloud value proposition is. So the big picture, I have a mission statement for myself, and this came about because if you walk in and you talk about like rip and replace and everything's got to go to the cloud, or you got to think about doing things in a completely different way, people get scared and they say we can't do that, particularly in the enterprise space. Startups, of course, can do it. So I came up with this idea that the key is to develop a revolutionary vision up front and then build an evolutionary path to get there. And that lands much more gently. People, particularly in the enterprise, they'd like to do things better than they do, but they're saddled with decades of techniques and technology and you name it. And you need to show them, like I said, an evolutionary path to get out of the space that they're in. This is another theme. It seems so obvious, right? There is no change without change. But if you get involved, you know, in the enterprise space in particular, they want to be better, but they want to, quote, reuse their existing skills. Those two things are counter to each other. And so I figure out how to boil it down to a very simple statement, which is if you want to change, you need to change. It's that simple. And one of the things you have to do is start with yes. In this space, generally I'll bring up an idea. Continuous delivery is a fun one to bring up. You bring that up and immediately, you won't get to say another word for like half an hour as the room fills up with all the reasons why you can't do it. I think we should start with yes and move forward from there. And then another concept is that it's really important to treat the things that we're building as products rather than as projects. Sorry about the delayed clicking there, that was weird. Particularly the space that I'm in and where the big vendors come from, everything's a project. The thing with a project is it has a beginning, a middle, and an end, and everybody moves on. But really, if you think about the way application software, what the total life cycle is it does live in perpetuity, and that really impacts how you architect it, how you deploy it. Almost every aspect of it is radically different when you consider it as a product instead of a project. So this is kind of the mission that I'm on right now with my customers and sharing with you all tonight, hoping that you're going to join in. And this is the statement that made me put this slide deck together in January of 2010, which I believe when I showed it to Bill, he wanted me to come in and show it to the group. This was customer facing. I'd been on the team for about 2 months. When I went to training in November at what was called PDC at the time, now called Build, we sat down with the product group and they got up in front of us and they very wisely, they said in a very sage way, everyone has their definition of the cloud. And like an idiot, I went, okay. And then I started to think about how I wanted to talk about this new cloud thing in front of customers. And this thing went through my head and I went, wait a minute, this makes no sense. So I broke it down. So this is the definition of a definition, which is basically, it's a meaning of a particular word or phrase that we all agree means that. Everyone, that's all of us. So if you think about, oh, right, and when I bring this up, people go, oh, yeah, that's just semantics. So I'm like, so I threw this in here too, that it's the meaning of a word, phrase, or text. So I'm like, yeah, it is semantics. So if you look at the statement, everyone has their definition of the cloud or DevOps or microservices or whatever, it's semantic nonsense. And it's when you sit and you're trying to have a conversation, particularly with large legacy type of companies, and they think it's okay for them to have their own definition of cloud computing. As I used to say, if you think cars are for moving on roads and I think they're for moving on water, we're not talking about cars. We're not having the same conversation. So this is an origin point for this entire talk. I've become somewhat more, shall we say, strident about definitions and first articles. The world is full of people who think they understand what a thing is, and then they operate on that. They don't, a lot of, well, like with the cloud, that it was deemed okay for everyone to have their own definition of what it is. That's not acceptable. And then what I'm seeing now, 10 years in on all of this, is that things that had tremendous value, like cloud, DevOps, and microservices, have become so mangled that I think a key part of the conversation is to go back to the first articles, where we all started. And you can do that with cloud computing, and we'll go through that definition tonight. DevOps, I'll touch on that, and I'll share a link with you, an excellent blog post that goes through the whole history of it. Microservices, I'm going to do a little on tonight because it happens to be my total passion. Sadly, I'm spending more time talking to people about what cloud computing is and what DevOps are, that I don't really get into microservice conversation as much as I would like to. And then, because I didn't have any place else to put it, I threw this term technical debt in here, which I learned recently was not what I thought it was. We tend to view it as the idea of when we take a piece of code, for instance, and we work on it for years and we keep doing this, that, and the other thing, like running it on Windows XP while XP is going end of life, and we consider that technical debt. That's actually not what the definition is. When we came up with it originally, the idea was we all make decisions in order to be able to ship software where we make a compromise. And the idea is we make this compromise with the idea that we're going to undo that compromise somewhere down the road. And that's why we drew this analogy with debt. We take on the debt. Debt needs to be retired. Well, we skip the retirement part, and then you go 20 years on with taking on technical debt voluntarily, and now you have a mess. So since we were talking about definitions, I tossed this one in here kind of as intellectual interest for people, because you will hear the term. Before we get into technology or any of this kind of stuff, we need to understand what business problems we're trying to solve, and it's pretty straightforward, okay? I boil it down in a nutshell to better, faster, cheaper, but I'll break it down in a little more detail. Business people want to get things done in a time frame that's meaningful in the market. There's no point responding to a competitive threat after the competitor has stolen your market from you. You need to get things done quickly. There's no point in having software that you need to deploy. So for instance, take the Super Bowl. If you need to be ready on a particular date, you need to be ready on that date. And if your engineering practices don't allow you to respond to that, then you're not an agile organization, and it's going to hurt you in the market. Complexity is an interesting thing because companies like my employer like to talk about easy and seamless or simple. We want to make things simple. If the problem that we're solving is complex, we can go to irreducible complexity, but we can't actually make it simple. That's a false target. But we do need to manage the complexity of the business processes that we're automating, because fundamentally that's what we do, is automate business processes. In the big companies in particular, governance and compliance are facts of life. There's nothing we can do about it. We need to deal with it, which means we need to build it into the architecture up front and use capabilities that the cloud brings to us that make it a little easier. Lots of things turned out to be relatively easy if you just think about them up front rather than nailing them on after the house is already built. And then I hear a lot about cost. It's too expensive relative to what? That's the response to that. You know, you can take something as simple as an email server. It's expensive to run an email server or to use Office 365 or whatever. But what's the cost if you don't run an email server and you're trying to do business in the 21st century without it? So cost has to be relative to something. It can't be in a vacuum. Most of the conversations we get into with business executives wind up being like, it costs too much and they want it to be lower. And that's not really a goal that you can target, but it is a big business problem that we need to handle. So there are challenges to solving these problems. So excessively complex solutions that look like this, which ultimately lead to this problem. They wind up, the older a piece of software gets, no surprise, the more brittle it becomes. And when it fails, it tends to fail catastrophically. So this is kind of and I have a few of these things where they're just lists of like almost stream of consciousness ideas that I've come up with over the years. A lot of how things are implemented today are done in ways that when we had, you know, not much RAM, for instance, or hard drives that were small and slow, and things like this. And so we developed software techniques to handle resource constraints. It's generally accepted that certainly the resource constraints that we had in the 60s, 70s, and 80s are long gone. And yet we're stuck with these legacy techniques that we developed, to my mind, literally in the 60s, that are still dogging us and become business challenges. Same idea here. There are a lot of things that that they made sense at the time when we were resource constrained, or computers weren't very fast or whatever, or they weren't networked. But there comes a point when you need to revisit the kind of the principles that you built up your architecture on. And then of course, there's just human nature. I get into a lot of these kind of conversations and it's very, very difficult. The info security world now is replete with, we have to do it this way. I have a friend who's at a large company here in town. He has, I think he said he's managing over 300 non-functional requirements in the security space, every single one of them tied to a particular tool that they're currently using to enforce that security policy. And that's just not a good way to get after it. And it requires that all of us who are involved in these conversations, you know, become well versed in these in these talking points and how to push back on this legacy thinking. Legacy thinking was fine 20 years ago, but we need to bring it forward. So fundamentally, when I look at cloud computing, Andrew, you're saying legacy thinking. What do you mean? Anyway, go ahead and say it. I'll come back to it in a second. Legacy thinking, to my mind, is anything that was appropriate in the past but is no longer appropriate, and we need to bring it forward. We need to modernize the thinking rather than continuing to think about problems in the old way. Got it. So fundamentally, what cloud was really, really good at was solving problems of scale. It turns out if you're not addressing a problem of scale, it's a relatively expensive way to solve problems. But that's that's an economics conversation. So I break it down into 3 types of scaling problems. And I put this slide deck together, by the way, so that I can explain these concepts to people who don't care about technology. So you won't see really any tech slides in here in this next set. So this is an example of what a retail establishment looks like at the holidays. You can probably guess from the color scheme which retail establishment it is. Okay. And it turns out, and this slide, by the way, goes back to 2010. It basically manifests these what we would call compute scale issues manifest in 4 different ways. One of them is what we call the on-off pattern or the batch mode. So where you need a lot of compute and then you don't need a lot of compute, and then you need a lot of compute and then you don't need it. It's very expensive, again, in the legacy way of doing things, to have to stand up that full amount of capacity for when you have those workloads running and it just sits there providing no value and consuming electricity and space. So this is one pattern. There's the pattern where your company is growing very quickly. This tends to impact startups more than it does enterprises. But still, you need to be able to build up your capacity quickly in response to growing market conditions. There are many situations where if you can't keep up with the market, you're gonna, Gap had this in the early days with their website. They would run sales and then not be able to handle the traffic. And people would just not come back again. You would lose those customers if you weren't able to solve it. Unpredictable bursting is a model like if you think about weather forecasting. You're going to need a lot of capacity during a major winter storm, and you don't know exactly when you're going to need it. You can't predict it, as opposed to things like retail at the holidays or accounting during tax season and things like this. Funny story on the predictable bursting. We're having trouble convincing or educating our accounting people on why the big 4 accounting firms' consumption consistently drops in May. And that was just very shocking to them. We also have it with insurance companies who do open enrollment in the last couple of months of the year, and then they're processing it in January, and then in February their numbers roll off, and the accounting people get all upset because they don't understand these models. So it's very important to be able to have these conversations with business people. So the cloud solution is just have a lot of capacity available. Kind of the model here with the cash registers is, yeah, the cash registers are all sitting there, but they don't have cashiers in them. And you can scale up and down as your capacity goes up and down. So that's the analogy there for cloud compute. Then you have geographic scale that you need to deal with. AccuWeather was one of my early customers, and when they tried to expand internationally, they were having to backhaul all of the mobile phone traffic and all of the web-based traffic from Europe to State College, Pennsylvania, because that's where their data center was. So you can imagine the user experience in the other parts of the world was not that good. And that's what this is representing. And then eventually with cloud computing, because it's relatively easy to distribute your compute, as long as you make the architectural concessions, and then you now have a much better user experience and you can handle the geographic scale. And then the last one is storage. So I come up with a cute way of showing you increasing storage requirements. And then the solution is to just do it at massive scale, multi-tenant storage, and leverage this. And this has actually been, and particularly in the enterprise, storage has been one of the most successful parts of the story at this point. It's not a great business model for us on the vendor side, but the customers get a lot of value out of this. And you can see how companies like EMC are struggling with the old way of doing things, and now they're more in a commodity game because of cloud computing than they ever were in the past. So, if you remember, I started this with everybody has their definition of the cloud. I made the case why that can't be. And then it turns out that there actually is a definition of cloud computing. There are 2 flavors of it. One is from the US government and one is from ISO. in the international space, they're roughly the same. I put these slides together to talk about the NIST definition, the US definition. It's not substantively different than the other one, so I did not try to genericize the slides. So the NIST definition has 5 essential characteristics of cloud computing. If it doesn't have these 5 essential characteristics, it's not a cloud. It's probably something else useful, but it's not a cloud. So it needs to be on demand and self-service. These are key characteristics of it. You need to, in order to get agility, you can't have to go through a procurement process, for instance, or any kind of manual process. I will share with you that many large enterprises, they did this first with virtualization. In fact, Bill's former employer, they had a 240-day process from the time somebody said, I need a server, until they had the server. Most of that was process, accounting, requisition, all this kind of stuff. And when they went to virtualization, because this was going to speed them up and make them more efficient, they saved about 10 business days out of the 240, because they saved the part where they had to rack and stack a physical server. Everything else about the process was the same. For cloud computing, this automation is critical. It's key. And it also gets into how you do scaling and things like that through APIs. It all has to be automated. By the way, VMware's original vision for virtualization was exactly the same, just nobody bothered to do it. When I make a statement like that, I mean so close to no one that it's effectively no one. It needs to be elastic. I never really came up with good pictures for this, but this shows an example of a truck that can get bigger when the load gets bigger. Or we've all seen meeting space where you can move the walls around and get larger rooms when you need them. Okay, multi-tenancy. So the example here is back in the day, I don't know, I assume it's still this way. The New York taxi cab system, the cabs were shared by multiple drivers, and they came out of a common pool. Metered services, this is a key, and it's one of the ways that you work the cost model of cloud computing is that you need to be able to meter your consumption in small increments. One of the things that's missed in a standard cloud deployment model is to deploy a VM and turn it on 24/7. That's a very coarse kind of metering at that point, and it turns out it's very expensive. And then broad network access. So it is considered to be a distributed computing paradigm, and therefore massive network scale is required. So those are the 5 characteristics. You hear a lot of companies say, well, we have a private cloud because we have a fully virtualized data center. Typically in that situation, they don't have metered service, for instance. So they're missing one of the characteristics, at least one, and it's simply not a cloud at that point. So there are 4 deployment models. Everyone's probably heard these at this point. There's the public cloud where all the noise is. There's the private cloud, which is completely bastardized as a fully virtualized data center. The only difference architecturally between a private cloud and a public cloud is who owns it, and typically the scale of it. This message is only now, after 10 years, starting to be felt in the enterprise where they're actually starting to deploy homogeneous infrastructure that can be leveraged and we using cloud techniques. Hybrid cloud, to my mind, is a nonsensical term, but it is part of the NIST definition. And it's the idea of public cloud and either private cloud or on-prem infrastructure collaborating together. We used to call this service-oriented architecture, but people like this hybrid cloud term. And the marketing people these days love it. It's really, to me, it's a completely abstract concept that doesn't mean anything. But if you read all 3 cloud vendors and what is driving their success, you'll see we all insist that it's hybrid computing that's making the cloud real in the enterprise. And then community cloud is really more of a government idea where you would have like an intelligence community with a shared cloud, or the defense community. Some of you are probably snickering because of the Jedi news at this point, but that's the idea behind a community cloud. To me, these are kind of distinctions without a difference. But they are part of the definition, so I do bring it to the people. I also want to point out, and I've alluded to this a couple of times, this is the NIST definition of cloud computing. There are essential characteristics, there are deployment models, and there are service models. It is not this. There are not different essential characteristics for private clouds and public clouds. And this is a huge mistake that is, or misperception that has been in place for over a decade. I'm still railing about it. Like I said, people are finally starting to catch on to it, but it's led to a lot of churn in the enterprise world around what they think they're implementing, and it hasn't really helped move the state of the art forward. And there are 3 service models. You've all heard of these: software as a service, platform as a service, and infrastructure as a service. And I note here, the bottom 2 are really building block layers, whereas the software as a service, there's more of a correlation with the old model of, license-based software on a per user basis. We tend to call them seats. It tends to be a higher level of abstraction. And then a lot of times you can take a look at something like software, Salesforce.com. They sell it as, on a per user basis, but they also have APIs on it and you can leverage it as a platform. We of course have similar things as well. But for examples, I tend to go with the best known ones. Excuse me. So now we're going to get into what I call key themes. These are ideas that are part of the overall conversation, because that was cloud. And cloud's an interesting conversation, and a lot of the computer science behind cloud computing, which is basically distributed computing, has been around since the 70s. We just didn't have the hardware to support it, so we couldn't leverage it. And cloud computing with Moore's law and the economics and all that type of economies of scale have allowed those ideas to be practical now. Sadly, most of what we spend our time doing with cloud computing is the old legacy stuff that has nothing to do with distributed computing. And we'll talk about some of that in a few minutes. I have a couple of slides on that. So services, we just talked about, the software as a service, platform as a service, whatever. So it's a good idea, and it's actually, back in the day, this took me a long time to come up with a concise model of what a service is. So it's code and a contract is really what differentiates a service from any other type of application code. Okay, the contract will tell you what the service does, tell you how you can access it, so the URI, for instance, or actually where the service can be accessed is the URI. The how it's accessed is basically the API definition. I still find it kind of amusing that SOA was sneered at because it was so over-engineered, and it was. But when we did REST, we went to REST APIs, we said, we don't need all that fancy WSDL stuff and the contract, definitions and all that up front, until they decided that actually we do. And then we had to reverse engineer all of that with what was called Swagger, which is now OpenAPI. And loose coupling, I used to say this it was more of a cloud idea, but it's really a service idea. And it's really, really critical. If you want to stay out of dependency hell, if you want to avoid technical debt, if you want to maintain your agility over time, your services that you're building, excuse me, need to be loosely coupled. And that's, excuse me a second. Sorry about that, a little lack of preparation on my part. So the key, we have to avoid hard dependencies. What makes an application become a monolith is hard dependencies. And it's, boy, I'm ahead of myself here. And this is the only way that I have seen in all of the work that I'm doing in a customer-facing way. It is the only way to avoid creating a monolith over time. There is the idea of a well-architected monolith, by the way, where you can minimize the dependencies, but this is the real world we live in. And the people who conceived of the original architecture, and by the way, this is a flaw in Sam Newman's second book that's called From Monolith to Microservices. it assumes a well-architected monolith. And I don't know about you guys, but in the work that I'm doing, I don't find very many of those. I spent 6 months working with one of my clients trying to decompose their monolith. And one day I finally said, team, not only is your monolith made out of granite, it is also set in concrete. And I had them then start the work of getting them to consider rebuilding it from scratch, which is not an easy sell, by the way. Nobody wants to hear that. And this is another key thing for loose coupling, and we violate this constantly. The internal state of a service cannot be exposed outside the service. And the reason that is so key is if the internal state is understood, if you need to change the internal structure of the state, you will break everything that needs to know about that structure. And the only way to avoid this tighter coupling is to have the API and the internal state that comes through the through that API is completely abstracted. It's interesting if you look at something like what's it called, the Open Data Standard. I'm drawing a blank. You actually do queries against internal data structures within the service. So you're pretty explicitly exposing the internal state. So this is a technology that shouldn't even exist because you're almost guaranteed to be creating monoliths with it. And then for those of you who've taken any time to study hypermedia, it's very interesting, it's intriguing, but it's a complete rewiring of your head to be able to think in the way that hypermedia requires. So I think we need to walk before we run, and what I've taken away from the hypermedia ideas is that you basically have 3 forms of state instead of just 2. One inside the producer, one inside the consumer, and then the representation of the state across the wire, and you map at the APIs. And again, yes.
Oops, sorry, I was trying to find a theme. You want to finish your thought, then I have a question on the slide?
No, go ahead.
On the hard dependencies, of course, if you're building cloud native applications, you have the option of taking dependencies on cloud services of anything. You know, in the Azure platform, for example, you can use storage queues or service bus or event grid or SQL DB, Cosmos, anything. You pick your thing. Just curious what your thoughts are about that sort of coupling, because you're taking a dependency on it. Certainly, you're not compiling, event grid into your application, right? Because it's an external service. But I'm just curious how you think about the dependency aspects of taking a dependency on cloud services, and can we be sure, for example, that those are stable over time?
So I'll answer the second part first, and the answer is no, and you shouldn't, because you can't. I believe, and so the database tier is is much easier for me to answer that on. I believe the data tier should be abstracted by the application architecture completely. If you look at the original 3-tier architectures, from the 80s, there was this idea that you had these 3 tiers and that you, in principle, could swap any of them out, particularly the data tier. But once the middle tier takes hard dependencies on the data tier, you're just hosed. So the way we get around that, right, is to abstract that interface between the two. Now with service-oriented architectures, we would create a service layer in front of the data tier, and everything is abstracted through that. And at that point, you're now free to swap out your different cloud services at that point. Does that make sense?
It does. So basically, you're insulating yourself.
Correct. You have to. And there's a very interesting, I have a reference to this book at the end. I don't know if any of you have heard of Yuval Lowy, and he has a book that he's written called Writing Software. His company, I think, is called iDesign. Let's just say he's extremely self-confident. He has come up with an architecture technique, which he refers to as the method. but I saw my own techniques in it. I just hadn't formalized it. And it's an architecture technique where you try to anticipate where what he calls the areas of volatility are. For instance, I mean, I designed actually the first thing that I implemented on Azure, I had actually implemented on a Linux host previously, and I very, very deliberately abstracted the data tier. And so when I went from MySQL on the Linux host to Azure DB at the time, or SQL DB at the time, that layer of code was very tightly held, and it was relatively easy to transfer it over. And this is critical with any application, any big application. You need to anticipate that it's going to live for years, if not decades. And if we've got enough history now, we know that things are going to change. And Bill, to the point you were asking about taking a dependency on a cloud service, we don't promise to never change them. We don't promise to never do breaking changes. To my mind, the REST API approach that we take, that Microsoft takes, and I'm assuming everybody else does too, is actually not particularly friendly to versioning and keeping track of different versions and how you do that. And so it falls to us on the app side to abstract that properly.
Interesting side note on the REST APIs. I've noticed some folks. So the SDKs are much easier to consume than the APIs. So if you're dealing with storage, for example, there's a nice clean SDK that adds a lot of value.
But then we broke it, right?
Well, I was going to say some people avoid using it and they go directly to the REST APIs just because it's too hard to, in their model of the world, it's too hard to keep up with changes to the SDKs. The SDKs have had a lot more churn over the years than the REST APIs.
Correct. Right. Because as we all know, when we write, there's that old adage, you should write your code once, then throw it away and do it again. And I heard recently it takes 3 times. So yeah, sure. We took a stab at it when it was just, the simple blob storage, table storage, and queues. And that wound up being insufficient. So we've probably changed it twice, if I remember correctly, which, that impacts your code. Now, in theory, you could even abstract away our SDKs. At some point, we have to make the trade-off over how much work we want to do to keep ourselves insulated. And interestingly, because there is this fantasy about no vendor lock-in, or what are we calling it now, multi-cloud? And I actually don't have anything in here. I consider that to be a nonsensical idea, but everybody loves it. If you want to do multi-cloud, if you want to have cloud independence, you actually have to do all of this abstraction stuff. I just think there are better reasons to do this abstraction. And then you also need to decide, if your data tier changes, is that such a major impact on your application that you'll live with the recoding effort that has to go into it? So lots of trade-offs to be made in this phase. I'm just trying to, I know that this coupling thing is what leads to monoliths, which leads to a lack of agility in the code, which leads to a lack of business agility for the organization. And it's going to kill companies now, because I've written in the past about it takes a certain amount of time to respond to a competitive threat. And because of the accelerating pace of change, there's less and less time to actually respond to a competitive threat. And these companies are going to die when they can't do it. So these concepts are key. So Michael, I see your comment there. Yeah, that's a big topic.
What you have to distinguish between the fact is that in the application domain, you are going to have coupling that you can't get away with. All right. If the rules of accounting say X, Y, and Z, or you have 3 dimensions of space, that's a essential piece of coupling that you'll never be able to do away with.
Would it be, but would that fall into the coupling between services?
Well, it depends. For example, if let's say you had a service that checked the to make sure that your audit was in compliance with the generally accepted accounting principles, and you had a separate service that, just for the sake of argument, came up with the audit. That's if the general principles of accounting change, you can't remove that dependency, and that's
an external dependency. Isn't that an external dependency then?
Well, when you look at the classic literature on loose versus tight coupling, that's the distinction that you made. And then to go back to your original point, yes, you could say that, but now we're quibbling over definitions.
Right.
What I'm trying to
well, you and I would never do that. Come on.
Right, never. But the point I'm trying to make is that very often when people start to think about we have to make everything loosely coupled, and they try to loosely couple things that are intrinsically coupled by the application domain.
Yeah, no, that's fair. And in a sense, we could leverage by analogy the things need to be as simple as possible and no simpler.
Correct. Yes.
So they need to be as loosely coupled as possible and no more.
If we didn't have coupling, we wouldn't have applications.
Yes. So yes, philosophically, I agree with that. To me, this is about monolith avoidance when I'm harping on this particular concept in this place. But your point is well taken. Okay, that's what I like. Feedback. So I really wasn't going to get much. Oh, that's right. I forgot this slide's broken. I don't want to spend too much time on microservices, even though it's like I actually think microservices have the ability to really revolutionize how we're doing things. However, there's a mental block that kicks in really hard and really fast on them. So I'm not going to spend a lot of time on it. The reason I wanted to touch on it, this idea of definitions and stuff, people will say things to me like, the micro really doesn't matter. Yeah, it does. It really does. They try to make out like microservices are really no different than service-oriented architecture type of services, which to my mind, most service-oriented architecture services wound up looking like a collection of monoliths rather than actual microservices. So the microservices by function need to be small, and they're small not only in the scope of the work that they do, but also the size of the teams that actually support them. And no, it doesn't mean that you need a separate team for every single microservice. A single team can manage multiple microservices, but that microservice is only managed by that team. All right. And then there can be no sharing of state, by which I mean there can't be a shared data tier between two different microservices. Of course, to have an application, you need to be able to exchange state information, but that goes back to the hypermedia discussion about bringing that state across the wire, in an abstract form. And that piece of state has to be managed by only one microservice, and any other entity that needs access to that information has to ask that microservice for it. So those are kind of the general principles around this. It's interesting in how it's evolved just in the last 5 or 6 years since it started. There was a time when we looked at having a distributed data tier. Now I think the performance of the data tier is improved to a point that you can actually have a shared data tier, but particularly with respect to write access, that has to be delegated to a single microservice. So that's a key concept. So this diagram, and if you can read the URL at the bottom, comes from the Microsoft Documents site. This is actually an ancient diagram that used to just have web APIs on it, and before that it had web services. This I do not consider to be a microservice architecture. I consider this to be a traditional web service architecture with the word microservice liberally sprinkled onto it. So this is a very common way that people view it. This isn't correct. The proper way to think about microservices is in this kind of a model. And this is actually a diagram that came from Red Hat showing their service mesh idea of how they communicate. So you really want to think of a sea of small microservices all communicating together. Now, this is where people get messed up. Excuse me. Because if you try to do this manually, it's really complex, which is where the idea of service meshes came from. I'm not getting into that tonight, but there are techniques to manage the complexity of the communication between all of these microservices. And that's really all I want to say about it tonight. So, I did give my little thing at the beginning that goes into cloud computing is interesting. I started down this path, I didn't finish it. Cloud computing is interesting, but in and of itself, it doesn't actually solve all of the problems that we discussed at the beginning. You do need DevOps, which is your way of actually taking code from a developer's desktop and getting it into production in a reliable way. As part of DevOps, we'll talk briefly about continuous integration and continuous delivery. These are techniques that tend to impact the developer world more than the ops world. You have security, the security lifecycle that needs to be part of this automated scheme as well. And then you have microservices, which I was just talking about. Those are how you take something that starts with cloud computing and then ultimately becomes a modern architecture for a business agile piece of functionality. So we'll talk about DevOps here as a key theme. And you hear a lot of talk about DevOps and culture. And this is where I had another one of my epiphanies not all that long ago. Culture follows DevOps. You can't change the culture in order to establish DevOps. DevOps fundamentally comes down to two things for me, and I'm not hung up on the order. I'm just happen to be showing them to you in this order. It's automation. Historically, the tooling that we have would be used to automate a human process. We need to change that, because in DevOps, we need to invert that, where the tooling is there. Well, I'll show you in a second. The processes that you're automating need to be designed to be automated. They're not manual processes that you are then automating. And that is the culture change that you get, okay? And this is a quote from a Google engineer back in the days. And he basically says, if we are engineering processes and solutions that are not automatable, we continue having to staff humans to maintain the system. Automation, by definition, is designed to not have humans involved. Otherwise, there's no point to it. And the second aspect of collaboration, and we'll see how many people I can offend with this slide, it is a collaboration between development and operations. I have another friend who slapped me because originally this slide said development with operations, which nominally implied development in the top position. So we modified the words because words matter. And there is this historic wall between development and operations. We talk about throwing things over the wall. And DevOps is about stopping that. So again, this is a culture change. If you tear down the wall and you start to collaborate between the two teams, you will then have affected a culture change. So, some detail, no more throwing it over the wall. For my entire career, we've talked about how we on the dev side would build the code and then we'd throw it over the wall and then the ops guys would figure out how to make it performant and secure. So we need to stop that. And by the way, it turns out in the current world, the throwing is going in both directions because the ops guys decide what infrastructure we can have and they throw that back over the wall at the dev side. And that is also flawed, and I'll talk on that briefly later on.
Mark?
Yes. Yes.
So is another version of this, you mentioned it as dev and ops working hand in hand harmoniously, no throwing over the wall. Some teams want to eliminate basically a separate ops function and have devs manage the ops side of their they own, the dev team owns the service, yes. Cradle to grave.
So I came up, I have an amusing line on that. There are three constituencies involved here: the business, dev, and ops. And each of them thinks the other two are idiots. Okay. So I think one of the things that we have to start doing in this new world order is we need to respect the subject matter expertise of the other teams. So I would balk at the idea of dev doing ops. In my understanding of history, there were some startups where there was no ops, so the devs wind up doing ops. And you'll see in a minute that I actually thought at one time that was the origin of DevOps, but it turns out it wasn't. But I myself would not, I wouldn't necessarily go that way. And by the way, site reliability engineering, which is how Google does DevOps, is staffed all by developers. All of their SREs are developers, but they're like developers plus. They're developers with ops knowledge. So if that's what you're referring to, that is a very possible outcome. Practically speaking, in the enterprise, which is my focus for obvious reasons, the ops guys aren't going away. They do create separate DevOps teams, which it was actually one of my clients who pointed out that that is considered an anti-pattern. And now I fully understand why. So that needs to go away. In fact, this particular client showed me a Venn diagram one day that had dev on one side, it had ops over here, it had DevOps here, and then this big elongated thing that was labeled SRE. And so they were going up in complexity. Things were not getting better that way. And I'm actually still working with them and trying to help dial that down. So no separate DevOps teams. And this is a key one. This is a big change. Application architecture needs to lead infrastructure architecture. From a theoretical / academic perspective, I would have said this was always the case. Practically speaking, though, you can't stand up an on-prem data center that can support any architecture that we can dream up on the app side. But with cloud computing, with its building blocks, we actually now have the ability to figure out the optimal application architecture and then drive the infrastructure implementation with that. And then the infrastructure as code techniques that we have make that even more practical to do that. So that's DevOps in a nutshell. I mean, it wasn't much, but that's because I boiled it all down to automation and collaboration, and all the rest of it are ideas that are concocted by what I call the DevOps industrial complex, because between the analysts and the consultants, they need something new to sell every year. So they keep coming up with new ideas, and you can drive cultural transformation, forever. In fact, we came up with digital transformation, so we have something else to talk about that doesn't exist. So yes, Netflix definitely has that method. I agree. So first articles, like I said, definitions and first articles matter. I mentioned this is where I thought, I had heard this through the lore, that these were practices developed by developers who had to do ops. I'm not saying that that wasn't out there. I think Netflix actually did, and many companies like Netflix actually did come up. And this is another thing, and I don't have this word in the definition list, but to my mind, and I think I've successfully won all the arguments I've had on it so far, there is a difference between the enterprise and companies like Netflix. They're both large, so they have that attribute in common. But if we look at, particularly those of us that have done both, they function very, very differently. And so my world is helping to transform the enterprise. And I'm not, I think the other side, the Netflixes and all the born in the cloud companies that we talk about, those guys are pretty good at taking care of themselves. I hear a lot of them still like to do things in the old way because that's what they were taught in college, but they figure out really quickly that those techniques don't hold on. Was somebody on our team here, was it Carbonite at one time? I can't remember.
Yeah, that was George.
Okay. Carbonite learned the hard way of what happens when you take traditional scaling methods that you use, that you're taught in college, and then try to apply them in the cloud, because they had a massive surge in business when Google lost a bunch of inboxes, about 150,000 inboxes, and the experts told everybody you need to be backing up your Google inbox. And Carbonite had a solution for that, but they could not handle the workload. But they figured it out real fast and they survived, and it was all good. So in reality, and this is the blog post I referenced, this Tom Garrity piece, which goes into a lot of history of DevOps. But where the term came from, it evolved in 2008, 2009, where a developer and an ops guy got together, and the ops guy was the one who was frustrated with the friction between the two teams and also saw the benefit of the tooling that the dev side had available and how that could be applied to operations problems. Okay. And so that's where it all came from. That's where it started. And it's important, particularly when you're conversing with an enterprise team, that you have this history available to you, because it's much less threatening to the ops guys if they think it was their idea. All right. Here's another idea. Automated testing is not a nice to have. I had a conversation with a customer a few weeks ago. We were talking about DevOps. I was explaining all these ideas. In fact, I used more or less a version of this slide deck. And they interrupted me at one point and said, well, we're doing all of those things, but they're not automated. Trying to make the case that they were doing DevOps. And so I said, are you doing unit testing? Well, no. So they weren't even doing automated testing. And automated testing, you have to do it. There's just no two ways about it. And it's really, really hard. And it's really hard to reverse engineer into existing code. But if you're going to say that you're doing DevOps, you have to have automated testing. And then this is a comment I've had in here for a long time. I just changed the tense of it today, as a matter of fact. The tooling that we use can be imperative or declarative. A lot of people are more comfortable with imperative techniques. However, if you're thinking about automating infrastructure, you get into all the same kind of bug problems that you get with imperative programming on the application side. Also, imperative can get really unwieldy at scale. So there are these declarative techniques. Now, I've met many developers who it takes them a long time to get comfortable with the declarative way of thinking, but it's worth the journey. Microsoft, because of the scale that we work at, is doing almost everything declaratively. We provide a lot of imperative capabilities through the Azure CLI and the like, but the way we will recommend that you do things is either with something like an ARM template or with Terraform templates, and just using those automated declarative techniques. So I break it into 3 pipelines. So there's what I call DevOps for applications, and I'm not going to read these slides to you, but I'll try to go slow enough that you have time to read them. The continuous integration idea, which is the idea of keeping your code always buildable. Okay, and part of doing that is to check in your code frequently, to not do a lot of branching, and to have automated build processes, including your unit testing framework, so that each time you do a check-in, you know whether the code can be built at that point. And there are organizations that actually, you're not supposed to go home if you've checked in code and broken the build. Continuous delivery is the idea that the application is always deployable. Not that it will be deployed, but that it always must be in a state where it is deployable. There are organizations, particularly the born in the cloud organizations. Trying to remember if the Amazon number, and I mean Amazon, not AWS, the Amazon number was something about 1,100 deployments a day, I think. If somebody knows that a bigger number than that, feel free to put it in the chat. But it's something of that magnitude. The techniques you use to do that are things like feature flags, where you deploy the code, but you don't enable new functionality, and then you enable it for a subset of users and things like that. This model works really well in the web world. It can work really well in a properly architected microservice architecture or application, sorry. But it takes a lot more commitment to do that kind of thing. But the capabilities are all there to deploy to production. There are many organizations now that have dumped their test environments. You check it in, it builds. If it goes down the pipeline, then it goes into prod with the functionality disabled. and then you enable it at the appropriate time. This also allows you to roll functionality back very quickly. It's also the way you handle changing APIs between services. Because as much as we would like to say that the APIs are immutable, that's not the real world.
Question?
Yeah.
You, in the continuous integration part, you mentioned not using very many branches. What's your thinking there about the impact of branching?
And this goes back to Jez Humble's original book on the subject, which is actually on continuous delivery. There's an integration books on it as well. The idea is when you branch a lot, you introduce complexity. The idea is not to not branch. You can branch, but they need to be short-lived. If you need to go outside the mainstream of the code and work privately for a little bit, it's fine. But you need to minimize that. And the intent is that the bulk of your work is actually going to be done on the main branch.
Thanks. I buy short-lived branches as a good proxy for few branches.
Right. But the reality, and I learned, there was a friend of mine, he was he became a big-time project manager, and I remember talking to him one Saturday morning because everybody had a feature branch, and then they had this big integration phase back into the trunk, and it just blew up. It just completely melted down. I have a client today that they're getting better, but for a long time, it was like they were maybe 50-50 with whether they could do a merge and deploy. And they were, I think, on a bi-weekly cycle. So these are the techniques that people smarter than me have come up with for avoiding that kind of integration hell that so many organizations were going through. There's also another factor that we're trying to get here to is that we would like to have better than a quarterly release cycle. And most organizations have a lot of difficulty. And one of my clients is doing a semi-annual release cycle, and it is not enough to keep up with the pace of the changes that their customers are demanding. All right. And then the last bullet here is about observability, which is basically meaning how these applications behave needs to be observable when it's in prod. And we as developers need to basically build that in. So that's what this aspect is in DevOps for applications. I'll touch on this in a little more detail in a minute. Then there's the infrastructure pipeline, so the so-called infrastructure as code. Site reliability engineering can fall into this. As I said, SRE is how Google does DevOps. I've seen that it's written down somewhere. Infrastructure as code is key. And when you get into organizations that are used to traditional ways of deploying infrastructure, the whole pets versus cattle conversation and how you patch, for instance, it's just a total mind twist. Bill, I'm not going to use your expression. But infrastructure as code is a really, really key part of implementing DevOps, because not only does your application need to be able to be deployed, tested and deployed quickly, your infrastructure does as well. That world from a tooling perspective is less well developed, but it's coming along. And then we hear about monitoring and observability. So it occurred to me, monitoring is a verb. It's something you do. And observability is an attribute of the system, which basically things that are exposed so that you can monitor them. And that's a code thing. And then these are the three categories of things that need to be exposed. Tracing in a distributed system is pretty mandatory and non-trivial. So I find it to be an interesting topic. I've got an application I need to wire up with it at this point. But it's definitely non-trivial, but really, really important so that those SRE guys can actually figure out why things aren't working in prod. And then there are containers, which are going to save the world, right? We're going to containerize everything, and all of our legacy apps will become wonderful in the cloud and all that kind of stuff. And all that snark is completely intentional. And I'll talk about containers in a few minutes, but they are a fundamental part of how you deploy the applications. You do need to containerize them, and then the infrastructure side manages the containers. And then there's the DevOps for security. You'll hear terms like DevSecOps, which is talking about how Dev and Ops will take on the responsibility for security as well. those of you who've heard me talk in the past, you will know that, you will have heard me say that security is not a cloud problem. I'm fascinated by all of the big financial services companies that we do business with who insist we have to do security exactly the way they do it, and all of them have been hacked multiple times. So, but security is a very interesting and important topic. We do need to shift left, which is this intention that the developers need to be part of designing secure code. There is still a tremendous amount of conversation in this industry about making it simple for developers so they don't have to worry their pretty little heads about all of this. As a developer and an architect, I'm calling nonsense on that, and this is something that we need to take on first and foremost. You have to design for security and you have to test for security. And these tools are coming along nicely in terms of doing even simple ideas like all the libraries that we include, the NuGet libraries and stuff. They have to be scanned because they're finding vulnerabilities in those all the time, and somebody needs to throw a flag on the play if an insecure library is rolling out into production. Operating system patches, all this type of stuff need to be accounted for. And this is a really key idea. It's definitely important in security. I find it kind of generically applicable. We need to focus on what needs to be done, what the what requirement is, not the how requirement. And I mentioned, my friend with the 300 non-functional requirements basically defined in terms of how to do something rather than what it is that needs to be done, and leaving the flexibility for, say, the native capabilities of a cloud to handle that functionality rather than forcing legacy tools and techniques into the cloud. So do you want me to talk about shift left, or did I make it clear?
Actually, that thread appeared before the shift left showed up on your slide. Jason may have more to mention.
Oh, okay. All right. I didn't. All right. Well, that's good synchronization. Jason, you can unmute instead of typing. We're recording. So I'm not going to spend much time on containers. I should have linked to this book that I read on it. It's fundamentally OS virtualization, which means if you get down and you study containers, it's a Linux process. It's an OS process, is all it is. I read a book on actually Kubernetes security, but the first few chapters, it was by a woman named Liz Rice. She writes very well. First few chapters were about how containers are built using the Linux capabilities. We should all bow down to Docker because the morass of stuff that you need to do to build a container that they automated is really kind of brilliant. No, it wasn't, we needed orchestration too, but that does not take away from the brilliance of what Docker accomplished with containerization. And by the way, containers go back to Sun's efforts to do virtual PCs in the Solaris world back in the 90s. That's when the original hooks got put into the Unix kernel at the time. It's a portable unit of deployment, and that is very key. There is a principle, and I think it's in Humble's CD book. I've read it elsewhere too. You're not supposed to store binary artifacts over time. You're supposed to store all the information so that you can rebuild a binary artifact, which is really tricky because that includes the tool versions that were in place at the time. With containerization, you can actually pack everything together into a single Docker definition. And it's very interesting how it's done. You include the tools in the Docker image when you load it in. The tools run and build your code. And then there's a layer where you then strip the tools back out of it to shrink the size of the container and leave you only with the application bits. So now you have your binary output. It can go into a repository. It can be rebuilt at will. And exactly the same bits will run in dev, will run in test, will run in prod. I almost pulled this bullet because this is kind of part of the marketing around virtualization without the need for a full virtual machine. It's not really, particularly with hypervisors. virtual machines are much more secure. They're much more isolated than a container will ever be. We're finally getting things locked down. It was actually not hard for application code to escape from a container and get into the rest of the system. We're tightening things up. The practices are known now. But the fact of the matter is containers do not provide you the isolation that a virtual machine does. Typically, you would put one service per container. And then you can, well, in the Kubernetes world, you have pods, so you can take the container and its communication container running side by side, and that can become a unit of deployment. So there are a lot of handy things you can do architecturally, but it all comes down to this ability to just package up your bits and it really comes down to a packaging technique. So I'm going to talk briefly about something called system containers and application containers. If you read the original container work, the word lightweight appears a lot. But then the ops guys got hold of these containers, which were going to save the world. And they decided that they needed to put everything inside the container. So the Windows Server core, without ASP.NET loaded, without IIS, across the wire, it's 1.3 gig and it expands, I believe, to about 5 gig. This doesn't meet any definition of lightweight that I'm familiar with, but it did allow ops guys to get in on this, what is fundamentally an application streamlining technology. So we renamed it. Now we have system containers, which are huge, and application containers, which are the original lightweight containers. The security book that I mentioned, she explicitly in the preface says, we're only talking about application containers here.
Another comment, Mark, on your
Yes.
fourth bullet. I would add this is about versus virtual machines. I would add that another really valuable facet of the container is the density of deployment. So it may be less secure in certain sense than a
Yes.
VM, but one of the plus sides is you can fit more of them in the same amount of resource and save money. And that's a big deal.
That is correct. And I would be fine, and I'm fine with that from an application architecture perspective. The problem is that that same argument is being used with system containers and it's not valid. So it works great. You're 100% right. With application containers, that is absolutely a value for you. You get much better packing density and utilization of your physical nodes than you can with a VM. In fact, those of us who have been around the Azure world for a long time, we know that one of the problems with the original cloud services is that the granularity was too coarse for scaling. You know, you had to go by a one core VM was the smallest you could scale by, and that was too much for a lot of functionality. So yes, that's a great point, Bill. So what problems do they solve? I've sort of touched on these. And I'm actually not sure why. I wonder if that question mark is even mine, because I did borrow these bullets from somebody else. But it does provide portability better than any technique that we've had in the past. You can build up a VM image and use that as a unit of deployment as well, and it'll be consistent, but it's a little coarse, all right? But by having the same bits in each environment, you do eliminate this works on my machine problem. However, as with all things, there's work to be done. You have to inject the environment-specific information into the container, and there are techniques for doing that. Hard coding is not really a good idea for that kind of thing, but lots of people do that. There is an improvement in productivity. It typically takes less time to set up environments. And I'm not actually sure what eliminates debugging environment-specific issues would be, so I'm going to move on from that. Again, I borrowed these particular bullets. It is definitely a smaller footprint than VM, so to Bill's point, it does increase server consolidation for application containers. I find that to be a fairly false statement when it comes to system containers. And there is isolation, but like I said, pretty much process isolation. The Linux kernel provides you with all of the capabilities that isolate your processes from each other. So in that sense, it's nothing new. It's just a very convenient way to handle this functionality. And here again, for applications containers, they are very performant and they start up quickly, which if you have a highly scalable application is a really important capability. Using the aforementioned example of the Windows Server Core container, a 1.3 gig container is not going to be started up in any quick manner at all. So hat tip to my friend Michael Stiefel, who's out there. He actually did a presentation for the .NET architecture group about a month or two ago, where he went into and he used as a proxy for his explanation the challenges that the Massachusetts vaccine website had when it came up, and these 7 principles. And I'm going to recommend that you go listen to the recording of his presentation. But I wanted to touch on each of these ideas tonight in terms of things you need to do to build a scalable architecture. If you remember back in the beginning, I said that the cloud solves problems of scale. So you need to be able to build scalable architectures. One thing that I do with a lot of customers where I'm trying to bring them around on proper cloud thinking is I ask the following question. Would it surprise you to know that cloud hardware is fundamentally unreliable? And they have all so far answered the question exactly the same way, which is, yes, that would surprise me. It says a lot about the marketing, doesn't it? So you need to design for failure. You need to assume failure. Michael and I actually wrestled with this term for a long time. I think Netflix actually may have used this one first, but it's considered a negative term. But the point of it from an architecture perspective is the underlying infrastructure is not reliable and cannot guarantee availability. Our architectures have to take that into account. Failures cascade, particularly, this is kind of a distributed computing concept. And again, where the dependencies can get tricky. And to Michael's point about, what was it? Intrinsic, essential coupling. Where you have coupling, if you get a failure in the middle of it, it's going to cascade and you have to figure out how to get yourself out of it. I like this one, that there's no such thing as a transient failure. I think my first example with this was actually with an old SCSI drive back in the mid-90s, and somebody decided that a 2-minute timeout was appropriate. So when you were trying to troubleshoot this system, get this system working, and you had to wait 120 seconds to see if it was going to fail out, you learn quickly that these timeouts are completely inappropriate. And the point that Michael makes here is that you need to detect the failure quickly and treat it as a resource failure. And so the whole idea of retrying is kind of flawed, because if it's a system failure, there's nothing to say that retrying it is going to fix it, and you need to get it back into a place where usually a human manages to deal with it.
Objection, Your Honor?
Yeah, sure.
On point 3, I'm trying to grapple with the recommendation to not, if I'm understanding it correctly, are we saying that retries should not be part of your strategy?
No, not at all. It's the, you just don't want to do it for too long.
Oh, okay, no problem.
Is that a fair way to
actually,
summarize it, Michael?
There are some people, I forget the name of the book. I think it's I'm staring at my bookshelf. Oh, it's Release It. Very interesting book called Release It. I think he would argue completely against retries on the grounds that if you have you have resources that are scarce. There are just so many database connections, ports, buffers that you're using, and when you're retrying, and this is part of the reason why failures cascade, is that you're taking resources away from the rest of the system when you retry. So, for example, if the credit card system, this is a good example of essential coupling and retry. Let's say and an argument against even human intervention. Let's say you are Netflix and you want to charge the person's credit card. Let's say they pick a movie, or you're selling something better yet, you're Amazon and you're selling something and you can't get to the credit card system to make the charge. So what do? You don't recharge, but you use a policy method saying how big is the purchase, how reliable is the customer, and you just decide automatically to let it go through, and maybe you'll put it on a stack and try it later.
Okay.
So, I mean, there are people who argue that say, and people who have done significant developments, is don't retry at all.
Interesting. So my experience, there are a lot of scenarios where retry. So that's a big like application level policy that you're describing. There's a much more micro kind of view here. Say if you're trying to push a message on a queue or something like that, or access a database, it often is, as you know, I think it's it's pretty helpful to be able to try it a couple of times, maybe with an exponential back off. Not forever, like Mark said. You don't want to hang around for 30 seconds while you're in the middle of some red hot part of your system. But the small quick retry saves the even if your application can handle the cascade of failures, sometimes it has consequences that you are better to avoid if for lack of a retry.
All right, I mean, it's fair enough. I mean, look, ultimately it comes down to people using their engineering and architectural common sense.
Yeah.
All right, you can list all the principles you want in the world. These are not biblical imperatives. They're more than rules of thumb, because designing for failure, but even take design for failure, you can say, in your opinion, that certain failures are acceptable if you want to. I mean, I can't think of any good examples off the top of my head, but again, to go to back Mark's point, what you need to do is look at the business case and judge everything against the business case. And if we can do this and satisfy the business case, then fine. It's just that as your system gets more complicated, your retries that look so innocuous at one time can be deadly at another time. So, I mean, you just have to think about those things.
Yeah, and
100%, then I agree 100%. Right? There's no. What I was more reacting to was a rule that said don't retry. That's all I was reacting to. Yes. Nuance is important.
Oh yes, but I would agree that in the as you said, in the application layer, more overwhelmingly more likely than not, you should fail fast and not retry. In the system layer, I mean, sure, if you're putting something on a queue and you're in a background process, who really cares?
Yeah, because user experience is also a huge part of this.
Yes, absolutely.
Well.
That's a good point. Actually, it's an excellent point, because when you retry, and especially in scale, let's say you are working with a write process, so something you can't put on a CDN or something that's a write process that's going to a database. Well, as Mark mentioned before, with geographic scaling, then the speed of light comes into play, and the more you retry, the longer it takes to get back to the user. So that's another factor that you're right, that you have to think about when you decide you're going to retry or not. What's the user experience?
Yeah, and it occurred to me while I was listening to that, and I need to put this somewhere on one of the earlier slides. We live in a world where people are like always or never, and those two concepts don't generally apply in the real world, but we insist on doing it. So this was a great example of that. As a rule, don't retry. but there are exceptions where it makes sense. Also, empirically, you can discover, you can try retrying, and then if you find out that it never goes through, what's the point of retrying? You may as well fail fast.
I'll give you an example of how you use this. I mean, it shows you how long I've been programming, but when I first got started, there was a great controversy over using go-to statements because you didn't produce structured programming.
Right.
So what I did was I first established the rule that said I'll never use go-tos. And that instilled in me a discipline, which I eventually learned when I could use go-tos. But I did learn that.
My experience was with a college professor who told us to never use go-tos. I made the case that there might be places where you needed to. His point was there's always a different way. And honestly, to this day, I've never had to use a go-to again.
Well, yes.
But I accept that there were places where you needed it. And I don't consider assembly language to count.
Right, but you're correct for a good reason. But my point was, by adopting a policy of never using it and reforming my habits, I learned when you really had to use it. Because it's very easy to get sloppy when you say, well, I'll do this 90% of the time, and you're late, the deadline's approaching, you're tired.
You'll take on technical debt is what you're saying.
Yes, that's right.
So, all right, well, let us continue. That was a great conversation. And this reminded me, Bill, of what it was like to be in person, where we would just get a conversation erupting in the audience. It was great. So use a margin of safety. And again, this is a thing where the cloud has made this much easier and much less expensive to do. You know, you can over provision resources reasonably without, in order to build up your margin of safety without blowing out your cost model. So, so that's a key idea. And then, of course, eliminating single points of failure. Got to get rid of the SPOPs. It's amazing how many people don't really get this and they do it anyway. I like Michael's comment here to admit you have to build a distributed application. Lots of people are still trying to deny that, but that's what we're doing. And then this is an early cloud idea to degrade gracefully and predictably rather than just failing out. And we would see this. In fact, I think Michael used to talk about this in his CAP theorem talk, but also just in general, if you have an application that is becoming overloaded and you lose one of those resources, you can stay on the air. It's just your performance is going to drop rather than just catastrophically failing. And then my favorite, assume the rare will occur because it's going to. It will occur. And the number of design decisions every day that I see which assume that that's never going to happen, that's just a disaster waiting to happen in production. In fact, the ops guys should kind of mandate this from their side of things, that this is not allowed to, you know, you're not allowed to assume something will never happen.
A question on that before you leave that slide, if you don't mind, Mark. Sure. And maybe this is as much for Michael too, is there an underlying assumption that you have a horizontally scalable architecture?
No. The assumption is that people are very, and you can read about this in Kahneman or other places, human beings are notoriously poor at estimating probabilities. And when they think of consequence, in other words, we're all focused. Programmers have this bias that they focus on the case that works. You know, what's the path to success?
The happy path. Yeah.
The happy path. And you'll notice how many, I don't respond, but I would like to address this to the audience just as a honesty check. How often people check for errors when they call an API? And how many people have a actual strategy for dealing what happens when that error occurs?
Well, I'm assuming everyone does because we never see unhandled exceptions, right?
Right, except for the great exception handler in the sky. So because people assume that things will work, there's an intrinsic bias to say that will never happen. The data center will never go down.
Right.
The redundant, and forget about the classic cases where the farmer with the backhoe runs over the power cable.
Right.
Or, any one of a number of things such like this.
Yeah,
Black swans happen.
So Bill, were you targeting specifically the last bullet, or was there a more generic question you were asking?
It was more generic and maybe more tied to the first bullet, where I don't know if you're assuming that the hardware on which your compute is running, for example, could vanish in a moment, but you also want to not have meaningful downtime because of that, and not have single points of failure and degrade gracefully and such, more holistically.
So Michael's answer is I would say in theory correct. It doesn't mandate it. I think practically speaking that horizontal scaling is the solution to is the solution to all of these factors. Also on the first one, I want to also
just to add you could say that we just give up or have a policy. The point is not the horizontal scale necessarily. The point is to have a policy based on the business case, because as you always emphasize, Mark, you have to always, the arbiter of all these things is the business value and the business case. Because, for example, in the enterprise, you can tell your employees, well, the system is down for 3 hours every night, and they'll just have to deal with that. In the consumer world, you can't generally get away with that. So you always have
also, even in the enterprise space,
yeah,
and I've lived through this, they will want 100% uptime. The only way you can guarantee that because of these reliability issues is to make everything redundant. But then the decision makers find out that it's going to cost them twice as much to have 100% uptime when 90% uptime would be just fine.
Yes. Or 50 times as much.
Right.
Right.
I think one of the very first talks I gave for the Azure user group, I did a comparison of the reliability of the electric company compared with the reliability of what people demanded. The electric company, I don't think, gives you 4 nines, if I remember correctly. It's been so long since I looked at it. So you're, in some sense, when you demand 100% reliability, you're asking more from the software world than you actually deal with real life companies in the real world.
And one other thing I want to point out, because I started this with the unreliable hardware or unreliable infrastructure, it's not just actual hardware failures, which are possible. And as it turned out empirically, the hardware is more reliable than we thought it would be, but we still don't guarantee it. But we do rebalance. For instance, one of the things that all clouds do is that we may need to rebalance and move a VM from one host to another. And that VM is going to pause at that point. And if your software is not designed to handle that, which kind of falls into the failure category, or we may need to patch the underlying host, and that's going to cause a pause and things like that. These things you need to take these into account in your scalable architecture.
And certainly software failures fall into that. The only reason I mentioned the infrastructure is because that's where the illusion very often is.
Right. Fair enough. Anything else? Or should we move on? Bill's type. Okay. So recovery-oriented computing, which is kind of a nice phrase that we came up with. I think it came out of Stanford, maybe. What did we have? What was the other one we had? Design for reliability. In fact, I may have that as a bullet here. Stuff is going to break in the cloud. I think we've just covered that ad nauseum. You need to design for that all of those failures at all levels. You need to design for reliability, which is where you get into your redundancy and things like. See, it's one thing to assume things are going to fail. You also need to compensate for that to make the system actually reliable. Chaos engineering is a Netflix idea where you basically bombard your system to have random component failures in it of all magnitudes, and then see how your system behaves.
Essentially, what they're doing is testing in production. That's the important idea.
Right. Yes. And in the enterprise, they haven't even begun to wrap their heads around that, but we'll get them there. And then this concept of item potency, I could have put this back on one of the services slides, but this idea, because of these concepts where you may have network failures and the like, and a process may execute more than once, you need to get the same result, no matter how you do it. And so this is a really key concept in distributed computing design, is this idea of item potency. So real quickly, there's this idea of the 8 fallacies of distributed computing, which started out as 7. They came up with these at Sun, and then somebody else at Sun threw the 8th one on at the end. We can decide if it's necessary. These are really, really important for developers to understand. And it's why things like RPC, remote procedure calls, bother me, because they're specifically designed to abstract away the vagaries of the network. And that's a really dangerous place to go. So fallacy number 1, that the network is reliable. It is not. Fallacy number 2, that latency is 0. Michael referred to the speed of light before. And in public cloud computing, for sure, latency is a huge issue and needs to be accounted for. Bandwidth is infinite. Practically speaking, maybe we're getting there, but it's not. The network is secure. We all know that is definitely not the case. Although I am having more and more thoughts about, are we spending too much time obsessing over bad bits getting to parts of the network, when if we just design secure endpoints, it would be irrelevant. The denial of service attacks are one exception to that, where we do need to keep the network secure. Topology doesn't change. That's not a fact. There is one administrator, and this is really critical, because if you have multiple administrators, that means you can get countervailing changes being made to the network, and software needs to be able to deal with that. Transport cost is 0. There is a cost every time you go out on the wire. Chatty applications we know are problematic, and so we really need to, this is another thing that the architects and developers need to keep track of. It's also another huge danger in thinking that the network is not there, and that the latency is 0, that you think you can be chatty when you can't. Network is homogeneous, which really plays to if you do repeated operations of the same type, that you're always going to follow the same path. If you put any kind of latency dependent functionality in, you're going to get bitten by this. And that was the 8th one that was added way back. For anybody who's interested, here's the article in Wikipedia. It's got a lot of history on it too. And we're pretty much done. At this point, these are the cloud documents, the NIST documents from the US government and ISO from Europe. If you're interested in reading them, it's fairly dry reading. I don't really recommend it. I just want you to know that it exists, that there is actually a definition of cloud computing. This is a bunch of articles that I've read over the years. You'll notice that these 2010 Netflix tech blogs are still really fundamental about, they were actually talking about why they chose Amazon's cloud in the first place. And honestly, had our cloud been more mature, it might have been more of a horse race, but Amazon was definitely ahead of us in those days. And then what they learned in their first year of implementing it, all this stuff still is valid. And then here's the book I mentioned, Writing Software, by Yuval Lowy. And I highly recommend this to anybody who's architecting code. This is some really fundamental good stuff, to put it crudely. This one's fun. Can't remember what Steve's last name is, but he did a whole. Yeah, that's right, Yegi. And this was all, if I remember, this was all about how Amazon came to be service oriented, but he was at Google at the time when he wrote it. And if I remember correctly, that's what this is. So anyway, just some interesting reading for you. And with that, we're done.
Wow. Well, thank you so much, Mark. Let's open it up here for a couple of minutes for anybody has final questions they want to pose to Mark. Feel free to come off mute and let him have it. We'll give that a few seconds to see if anybody's going to take us up on that.
Yeah.
While we're giving that a minute, Michael, it was great to have you call in. Haven't encountered you in maybe since pre-COVID. Are you in the continental states?
Yes.
Or are you are okay.
I just came back from elsewhere. Where those of you who know me know where elsewhere is.
Very good. Well, we have some thanks for the presentation. So it looks like we're not getting any takers on further questions. So huge thanks, Mark. This was very energetic, and like I tried to allude to in the meeting posting and then the intro. You always get us to think. It was a good chat, and it was really great to have you so engaged as well, Michael.
Yeah, exactly. I had a good time. Thank you. I appreciate your setting the stage. And yeah, it's been a while since I did this one, so it was fun to bring it back out and get it updated. And I hope I did get some people thinking. Anybody who, hopefully, I might maybe even struck some painful chords, and you should feel free to reach out to me and we can have a conversation about it. And a lot of what I kind of disclaimed at the beginning, I don't think my employer is doing a great job getting a lot of these messages out there. And it's kind of my day-to-day life now working with my clients. I have said to one of my clients, I said, with all due respect, you don't have a cloud strategy, and he didn't disagree with me. So, these are messages that need to get out here, even as Bill's title alludes to, over 10 years in, and we're still having the same conversation.
And Mark, what's your Twitter handle?
I don't even use it that much. It's out at Cloud Biz and Tech. I haven't been really